However, in order to save time, I would not like to discuss the homework in detail on the blackboard. I will just collect them and we will briefly go through the solution, because for this lecture today I took slides by Bettina, who did it last year, and I enhanced them quite a bit with additional information. So I'm a bit worried that this may take us quite some time, so let's not waste any time regarding the homework. So I will just collect them, correct them until next week and give them back to you next week. Also, I already uploaded an example solution for this homework to our wiki, assuming that nobody will start with the homework 5 minutes before the lecture. Just give them to me in the break or now, or put them somewhere. Okay, and don't forget to write your name on it, of course. So let's just very briefly discuss this homework and how the solution for that would look like. So remember that we had a game graph and a recalculus formula, and our task was, first of all, to write down an algorithm which evaluates this recalculus formula, so it should compute the meaning of this recalculus formula, which is always a set of states. And then as a second step, you should execute this algorithm, basically, to compute the result, the meaning of this recalculus formula. Here is my solution. Remember that whenever such a recalculus formula has a greatest fixed point, then we can always transform this into an algorithm which looks like this. We start with the set of OR states in our game graph, which is called Q usually. And then, as long as this variable x changes, what we do is we compute the new value of x by evaluating the inner part of this recalculus formula. Now, in the examples we did in the class last time, this inner part of this recalculus formula was always just something that was very easy to compute. But this time it's a bit more complicated. Now this inner part of the recalculus formula contains again a fixed point operator, this time a least fixed point operator. So we will need a second loop in order to compute the result of this least fixed point operator. And remember from previous week that such a least fixed point operator can always be computed in such a way. We start with the empty set of states, and then as long as this variable y here changes, we compute the new value of y simply by applying the body of this least fixed point operator to the old value of y. And this is exactly what you can find here. So this is this inner part. Now, once we are done executing this inner loop here, then the result of this computation will be stored in the variable y. And this variable y gives us the new value of x, because variable y contains the result of this inner thing here. So this then also is the new value for the outer fixed point. So this is basically how you can transform also such nested recalculus formulas into algorithms. It's pretty straightforward actually, like playing Lego. Whenever you see a least fixed point, you always plug in your formula for your algorithm for the least fixed point and otherwise for the greatest fixed point. Now, once you have this algorithm, you are basically done. The second part was just to execute this algorithm, but this is quite a mechanical task. Of course, it's easy to make mistakes, but conceptually it's very simple how you do this. So much for the homework. Now let's turn to the content of